ever get that, like, cars of the future feeling? You know, when you see those self-driving cars just cruising around,
Yeah, yeah, totally.
like, they're seeing the world just like we do. But instead of eyes, they're using some serious AI. And that's what we're diving into today, a research paper tackling a big challenge in that AI world.
Hmm.
Specifically, something called semantic segmentation. Rings a bell?
Oh, absolutely. And what's really cool about semantic segmentation is it's not just about recognizing like, oh, there's a car, there's a tree. It's about labeling every single pixel in an image.
Whoa, every single pixel. So it's like this pixel is road, this pixel is confused pedestrian.
Exactly. It's like a super, super high resolution coloring book, but for robots.
Okay, I like that analogy.
And that level of detail, as you can imagine, that's critical for things like self-driving cars.
Yeah.
They need to know the difference between a fire hydrant and, well, a pedestrian, not just that there's something there.
Yeah, that makes sense. But I imagine getting to that level of like pixel perfect precision, that can't be easy. What are some of the challenges that researchers are kind of grappling with in this area?
Yeah. So one of the big ones is balancing that detail, right? That pixel perfect labeling with context. Think about how you look at a photo.
Yeah.
You instantly know, okay, this is closer, this is farther away, this is important. Early computer vision models, they really struggled with that.
So they were so busy labeling every pixel, they missed the forest for the trees.
Precisely. And it's because traditional convolutional neural networks, which are kind of inspired by how our eyes work, they often use what are called pooling layers. And you can think of these like shrinking a large image down.
Okay.
So you're shrinking it down, it helps identify the objects, but you can lose detail in that shrinking process.
So it's like a trade-off. You get to name the object, but you lose the nuance, the context.
Exactly. And that's where this paper comes in. It introduces what I think is a really elegant solution, and they're called dilated convolutions.
Dilated convolutions. Okay, I'm already intrigued. That sounds like something out of a sci-fi movie. What's the concept there?
Well, so imagine you have a window, right?
Yeah.
And this window can see pixels that are farther apart without actually changing its size.
Oh.
That's essentially what dilated convolutions do. They allow the network to kind of expand its receptive field, we call it, exponentially. So it's taking in a wider view, but without needing to sacrifice the detail.
So instead of shrinking the image down with pooling, which loses information, it's more like giving the AI the ability to zoom out without losing that initial sharp focus.
You got it. It's a really clever workaround, and it seems to give you both. It gives you the high-resolution output, but also that contextual understanding.
Now that's what I call thinking outside the box, or in this case, maybe inside the pixel. But how does this work? We've got these dilated convolutions. How are they actually using those within the neural network itself? So we're giving the AI this like wider field of vision with these dilated convolutions, but how do they actually put that into practice? Like within the neural network itself, what's going on?
Yeah, so that's where the context module comes in.
Okay. Context module. Sounds very official.
Right. It sounds very important, but it's quite an elegant idea.
Right.
So the researchers designed this module specifically to incorporate these dilated convolutions in a way that makes sense.
Okay, so break it down for me. What's actually happening in this context module?
So essentially what it is, it's a stack of convolutional layers.
Okay.
But each layer uses a larger dilation factor than the one before it.
Okay, I'm with you.
So you can almost imagine it as like looking at the same image through a series of magnifying glasses.
Oh, interesting.
Each one is sort of revealing a wider and wider field of view.
So each layer is kind of seeing the image at a different scale, but without losing that original crispness.
Exactly.
Exactly.
That's really cool. It's like the AI is getting this multi-layered understanding of the image with each layer.
That's a great way to put it. Yeah. With each layer, the network is understanding those relationships between the pixels at a deeper level, essentially.
So then it's building this richer context for making its prediction.
Exactly.
And that's where it gets really interesting for me, because I imagine building a new module like this, right, with all of its like magnifying glass layers, must come with its own set of challenges. Like, how do you even begin to train something this complex?
Yeah. You're absolutely right. Training a network with a context module like this isn't as straightforward as you might think. And one of the key insights from this research was how important the initial setup or initialization of this module was.
Okay, so by initialization, are we talking about like how you set up the network before you even start training it on data? Exactly. So typically when you're training a neural network, you initialize the weights randomly.
Okay.
And these weights You can kind of think of them as the importance assigned to different connections within the network.
So you're kind of setting the dials to a random starting position before you start fine-tuning them during training.
Yeah, you got it. But in this case, they found that random initialization just wasn't effective for this context module.
Really?
It wasn't really learning.
So they had to rethink that whole random starting point idea.
Exactly.
What did they do instead?
So what they ended up using is something called identity initialization.
Identity. Okay.
Yeah. And so instead of those random weights, they essentially start with the simplest possible setup, where each layer just passes information through unchanged.
Huh. So instead of that random noise, they're starting with pure signal. It seems kind of counterintuitive because, wouldn't you want to introduce that randomness to help the network explore different possibilities?
It's a natural assumption. But surprisingly, by starting with this kind of blank slate, it actually allowed the network to learn much more effectively how to use that expanded context.
Oh, wow. So it's like they gave it the structure to see the potential without dictating the outcome from the get-go.
Yeah, that's a great way to put it.
It's fascinating how this subtle shift in the initial setup can make such a big difference.
Absolutely. But of course, I know you're wondering, okay, but did it actually work? Did it work?
That's the million-dollar question. Give me the details. Did all this innovation actually lead to better results? Did it work? Did it work?
It did. It's my favorite part, actually. Seeing how these clever ideas actually translate into results. And in this case, the results were pretty impressive. They found that this approach, using this context module and that identity initialization we talked about, it significantly outperformed previous state-of-the-art models.
Okay, so we're talking a noticeable difference. It was significantly better at labeling those pixels.
Oh yeah, it wasn't just a small improvement. This was a significant jump. And here's what I thought was really interesting. It even outperformed methods that used additional techniques, like something called conditional random fields, or CRFs, on top of it to try and refine their results.
So CRFs, those are
Yeah, you can think of CRFs almost like a cleanup crew. So they come in after the network makes its initial predictions and they try to smooth things out and make sure everything is consistent.
So this new approach was so good, it didn't even need the cleanup crew.
Yeah, it seems that way. It seems like by directly incorporating that contextual information through those dilated convolutions, the network was producing results that were inherently more accurate and more consistent straight out of the gate.
I love that. Why overcomplicate things with all these extra steps if you can just build a good solution into the core?
Exactly.
But, this has got me thinking. We've been talking a lot about self-driving cars, but I have a feeling that this technique, these dilated convolutions, they have implications way beyond just that.
Oh, absolutely. Yeah, this is not just about cars that can see. This is about any task where you need to be able to understand fine detail and broader context at the same time. I mean, imagine applying this to something like medical imaging.
Oh, wow. Yeah.
You can have an AI that not only detects tiny anomalies in a scan, but it also understands how those anomalies relate to the surrounding tissue.
Right. That's incredible and way more accurate, probably.
Exactly. Or even think about something like analyzing satellite images, where you need to be able to see individual trees, but also understand the overall deforestation patterns.
It's like we're giving AI this whole new level of perception.
Yeah.
We started with self-driving cars, but it feels like a much bigger leap than that.
It really does. And I think as these techniques continue to be developed, who knows what other applications we'll find.
Right. It's exciting to think about. Well, this deep dive has definitely left me with a lot to ponder. One thing I keep coming back to is, what if we could train these super-powered networks, the ones using these dilated convolutions? What if we could train them directly on raw images from the very beginning?
Ooh, that's interesting.
No pre-training, no starting points, just pure learning from scratch.
Wow. It'd be like raising a child with perfect vision from the moment they were born.
Exactly.
Just able to see the world with incredible clarity and depth. It could revolutionize how we think about these models.
It really could. Well, I want to give a big thanks to our expert for taking us on this deep dive into the world of dilated convolutions. I don't know about you, listener, but I'm seeing the future of AI in a whole new light, and it is looking incredibly exciting.